Thank you very much, and thank you, the organizers, for inviting me and allowing me to speak here today. So today I'll be talking about finitely forcible graph forms, and the main idea of the talk is for you at the end to understand that finitely forcible graph forms can be as complex as any other graph form. So this is my main goal today. And this is a joint work with Jacob Cooper and Dan Kroll, and all of us are from the University of Warwick. So the talk will be as follows. Basically, I will start giving some definitions that you already saw on Dan's talk, but just to be self-contained this talk, I will recall some basic definitions again. Then I will be talking a little bit more of finitely forcible graph forms, and in particular, we see these two conjectures that Dan mentioned briefly. And then we would present our result that basically says that finitely forcible graph forms are as complex as any other graph form. And then I'll give a sketch of the proof, but like very brief sketch of the proof. Okay, so graph forms, as we also saw in this morning already, they are measurable functions from the unit square to the unit interval. Symmetric measurable functions. And basically, a standard way of representing these functions to kind of help to visualize the functions instead of describing every time is by such pictures. So you basically draw a unit square, and then each dot, like each point in the unit square, you color by a color, and white is representing when the function has value 0, and black is when the function has value 1, and like gray, it's all the values in between, the shades of gray. So basically this function, for example, whenever x plus y is bigger or equal than 1, then you have like the function has value 1, and otherwise has value 0. And in this one, for example, it's like half everywhere, like constant half everywhere. And a key notion that allows us to talk about graphs and graph forms is basically a sampling method, is the notion of W random graphs. And we say that a W random graph of order n, you will be taken in the following way. So you select any random points from the unit interval, and then you put an edge between these 2 points with probability given by the graph form. And in this way, you can obtain a graph that the structure will be resemble the structure like of the graph form as your order gets bigger and bigger. Okay. And now we are able to talk about graphs in graph forms. Now with this, we can define the notion of density of a graph in a graph form. And basically, we say that the density of a graph H in a graph form W is the probability that whenever I pick a W random graph of order the size of H, then I will see a graph isomorphic to H. And just to make sure that we are all understanding this definition, I have this example. Basically, this graph form represents when you have the disjoint union of 3 cliques of same size. And then if you want to see the edge density, basically you just need to pick 2 points, and they need to lie in the same clique, in the same black box here. So whenever you pick 2 points, the probability that they will be in the same block, it's 1/9. Have 3 blocks, edge density 1/3, 1/3. And if you want, for example, to see edge with an isolated vertex, you just need for the isolated vertex be in a different clique than the edge. So the same 1/9 for the 2 vertices, and 2/3 because you have 2 other cliques to choose for the isolated vertex. And because this basically is just disjoint union of 3 cliques, we already, like it's easy to see, but we also know the density of P4 is 0, like there is no P4 here. there's no way of sampling this. Okay, so basically now we are talking about densities, and we can now talk about densities of a graph in a graph and densities of a graph in a graphome. So notice that if we know the densities of all graphs, all finite graphs in a graph, basically this determines uniquely the graph that we are talking about. And the same goes to the graphome, like up to weak isomorphism, but determines uniquely the graph and the graphome. But in this case, what we have is like we need to know all this information. And the set of graphs that we're considering is finite. So basically, a natural question would be, what if the set of graphs that we are looking at is not finite anymore? No, it's not infinite anymore, and it's finite. Can I say something about the structure of this graph? And of course, like for example, if I just consider, for example, edge density, and I just tell you edge density is half, I cannot tell anything about the structure of this graph. But in some other cases, you could infer the structure of the graph, not the graph uniquely, but like the structure of it. So for example, if I tell you that the edge density is 1, you know for sure that it's a complete graph. And in the graphome language, you know that is the constant 1 everywhere. And also, if I tell you that the edge density is 1 minus 1 over r, and the graph is kr plus 1 free, then by Turan's theorem, you basically know they are talking about R multipartite graph, complete multipartite graph, basically the Turan graph, right? Like, and in the graphome language, you are, for example, if R is equal to 3, we have like this example, which is basically representing the Turan graph. Yeah, so basically you know that G is the blow up of AKR in this case. Yeah, so, and this idea here of defining densities that basically define uniquely the structure of the graph is exactly the idea of finitely forcible graphomes. So a finitely forcible graphome is just a graphome exactly that it can be defined uniquely by a finite number of graph densities. And yeah, so for example, in the previous slide, what I said to you was basically that this graphome 1 is constant everywhere, is finitely forcible, and you just need to know that edge density of it, and any other graphome that has this edge density will be the same as this one. Actually, it's weakly isomorphic, but it doesn't matter. So it's the same as this one. And the same goes for this graphome, so it's finitely forcible exactly because I just need to, any other graphome have exactly the same densities of K2 and K4 will be exactly this graphome. And so these finitely forcible graphomes, by the definition that basically you just need to force some densities, you already can see that they are already related to extremal problems because you basically are defining them exactly by these densities. And as Dan mentioned as well, so they have this close relationship with extremal combinatorics. And exactly because of this connection, this like it was main motivation of the study. And like we would like to really understand these objects. Okay, so another, but you can say like, oh, okay, this is very simple. I want to see more complicated. I want to see if there is more. And the examples of finitely forcible graphomes are the constant graphome, like P everywhere. And Dan already mentioned that predates graph limits, this result. Also, any step graph, Lovas and Shores, they prove that any step graphome is finitely forcible. So basically, what is a step graphome is you pick the unit interval, partitioning finitely many measurable sets, and then in each, between any of these two parts, you have a constant function. The function, the graphome is constant there in that part, like in those two parts. And also we have like lots of other examples of finitely forcible graphomes. And Lovas and Segedi, they they did a systematic study on these objects, and they come up with lots of examples of finitely forcible graphomes. And they also made two conjectures that basically say that this should have a simple structure. And formally, Dan already mentioned, the two conjectures are that the space of typical vertices of a finitely forcible graphome is compact, and the same space is finite dimensional. And this is basically just telling you that it's a simple structure. And if you don't believe me, like I will explain a little bit more what these two conjectures, like what this conjecture are saying, and then we will understand better, like that actually just means simple structure. So in order to understand these two conjectures, first thing you need to understand is like, what is a typical vertex? What is the space of typical vertices? And I will not explain this formally, but I'll give you some idea, and hopefully everyone will understand the idea. So basically, we say that a vertex is typical if you have a large enough, if you sample a large enough W random graph, there is a positive probability that you will see that structure of that vertex there. So in this sense, basically, for example, this graphome have 4 typical vertices. So this part here corresponds to 1, like this interval. This other interval corresponds to a second one. This is the third one, and this is the fourth. So basically, you have 4 typical vertices for this graphome. So basically, it's just the space of typical vertices is basically 4 points in this case. In this case here, we have disjoint cliques, and they are kind of halving their sizes every time. And basically, what we see is like each part here corresponds to a different typical, corresponds to 1 typical vertex in this space. And then here we have a countable number of typical spaces. And in here we have like an uncountable number of typical space, which you kind of also can guess that resembles a line in here. Lovas and Segedi, they show that every graphome can be assigned a topological space corresponds to its typical vertices. And an important observation is that if the space of typical vertices is equipped with an appropriate metric, then if it has Minkowski dimension D, this would imply that W has weak epsilon regular partition with number of parts 1 over epsilon to the D parts. Yes, and if you don't remember much more about weak epsilon regular partition or never saw this concept before, you can be happy because I will explain a little bit now what it is, what that I mean here. But basically, the idea here is I want to say that if the dimension of this space would be bounded, would be finite, then this kind of would not need too many parts in the weak epsilon regular partition, and therefore would be simple. But we will see a little bit more. So the notion of weak epsilon regular partition was first introduced in 1999 by Friesen and Cannon, and basically it says that if you have a partition of, so basically this I am introducing for graphs, and the same theory basically just translates directly to graphomes. And in a graph, if you have a partition of the vertex set, we say that this partition is weak epsilon regular partition if for any 2 sets S and T, we can approximate the number of edges between these 2 sets by looking at the edge density between any of these 2 parts and looking at the number of vertices from S and T in those sets in your partition. And if you approximate by this amount of this counting, your error that you are doing in the count is not too big. And basically this is kind of telling you that you can approximate any graphome by a step graphome, because you basically are picking parts, and then you pick the edge density, so you put between those 2 parts all the edge densities, and you say this graphome is not that different from this one. Okay, so, and we know that every graph and every graphome as well have a weak epsilon regular partition with at most this number of parts. And the upper bound was given by Fries and Cannon, and Colon and Fox also showed that this that is always a graph or graphome such that every weak epsilon regular partition has this many parts. So basically, this is tight. And basically, the number of these parts is basically how many steps in your graphome you like. How much do you need to refine it? And so again, if you have a little bit, only like not that many exponential number of parts, it seems like your graphome can be very simple. And so basically, the conjectures are saying like this is simple, but unfortunately, we already have negative results. That can fail to be compact, the space, and also can have parts, it's not finite dimensional. And I think I'll skip a little bit. So basically what these two results have in common, so basically we have like this graphome is the counterexample for the space being compact, and this one is the example of the weak, like that needs like a lot of parts in the weak epsilon regular partition. And what do they have in common is that actually the important part, what makes the conjecture false, is only these red parts, like these tiny parts. All the rest is basically to give a structure for you to create their parts and also to make it finitely forcible. And so looking at this, we wanted to kind of a framework that would be able to kind of, okay, so maybe we just want some framework to kind of embed a graph, like certain graphomes in this graph, in a finitely forcible graphome, and this is exactly what we were looking for, and we prove basically exactly this, that every graphome is a subgraphome of a finitely forcible graphome, and this would imply, as corollary of this, we have that basically we have the two other results because we have any graphome actually can be there, and we also generalize the previous result in the number of weak epsilon regular parts needed. And the ingredients of the proof are basically partitioned graphomes. These two techniques already were developed in the previous two papers, and the main new idea is not only this, but what I want to tell you today is basically how you can encode a graphome as a real number, and basically you can do this. So if you are looking at a graphome, you can look at it like the unit interval and refine it in number of parts. So basically, let's consider one part. If I refine the unit interval in two parts, I have like 4 squares and so on. And I am interested in the edge density in these squares in my graphome. And for example, here, like this part, the edge density is 0, 1, half, and half, and so on. So if I have all these densities, they define uniquely the graphome that I am talking about. And also, I just need, like, if I pick this for every square, I have a countable number of squares, and I have a countable number of densities that describe uniquely my graphome. And basically, it's not difficult to see that once you get all these densities, if you only have the densities as well, you can recover the graphome as well from these densities. So basically with these densities, since it's countable number of densities and these densities can be represented in a countable way, you can construct a real number by looking at these densities that represents these densities. And our result is basically then we encode the graphome that we want to force as a real number here. And this sequence of densities that we are representing, we are able to refer to these indices in here. And then we refer the dyadic squares, which is the squares that was mentioned of this part that I want to force here. And then basically, I make each part of corresponds to the graphome to have exactly the density that I want. And because it defines uniquely, the graphome will show up here. And the rest is just a bunch of technicalities. These are our graphome. The red parts are the only parts that change depending on the graphome that you want to force. And I am out of time, and thank you for your attention.
Thank you so much. Any questions? Yeah.
So, does your construction say about extreme combinatorial properties?
What, sorry?
What does your construction say in these graphomes are used for extreme combinatorial?
Yes. So basically, it says that the problems can be as complex as you want in the sense of these extremal results could be very complex in the sense that they could need like lots of parts in the weak epsilon regular partition, but also says a little bit more, which is kind of this result also like it's nice because it will be like was also used to prove something that you see in the next talk, which is nicer. And I don't want to tell you about this because you will see it. But basically, is it, and also like, which is really nice, is like, you can kind of now look at any graphome here, like from the whole space of graphomes can show up here, and this doesn't change much. So basically, you kind of have like a lot of freedom now, and you see that these objects that they thought would be simple because the main idea was like, yeah, extremal problems, maybe we can infer something from the graph theory and bring it to graph limits theory and bring it back to extremal combinatorics. It's not as easy as we thought, kind of. This.
So another question, is there some sense to the results saying how much you have to blow up? Like you're basically taking a graph on it, you have to shrink it down a lot to fit it into
yeah, but like if you think about it, you just need okay, it's a big number, but what is really nice is like, you just need a finite number of densities, and this kind of describes this structure that have any graph inside. So I don't know, I think this is quite cool. But yeah, I don't know if it answers, but this is it.
Any other questions? If not, we'll proceed to our next speaker.